Hi everyone. Can you hear me? Yeah. Okay. So yeah, I'm Daniel. I want to start by thanking the organizers for setting up such a nice event. I always love coming to Natal. And today I'm going to tell you about not so recent work on boson sampling with a linear number of modes, right? So if that doesn't mean anything to you yet, it will shortly. But basically, just take the stuff that Ernesto was telling you about and just like scale it super big. Okay. This is joint work with these people, including Mihalos Maniak, a good friend who is here somewhere. Okay, so let me start telling you what boson sampling is and sort of general motivation behind this kind of question. So, we all know that building a universal quantum computer is really hard, of course. So, like roughly 15 years ago, people started asking the question, what if rather than skipping straight to universal quantum computer, we instead ask, what is the sort of simplest experiment that you could do that would be a demonstration of like raw computational power in the near future, right? So forget using it for something useful. Can you just show that quantum mechanics works in a limit of high computational complexity? And this started roughly in 2012, and several different proposals of this kind of big quantum computational advantage umbrella appeared since then. So boson sampling is one, which is just based on linear optics. There's random circuit sampling. I think there is. Random circuit sampling and some other alternatives since then. And in this talk, I'm going to specifically talk about boson sampling. Okay? And its variants, right? So like standard Gaussian boson sampling and so on. Okay, so the idea of this talk, the outline is I'm going to tell you what boson sampling is, just kind of define the model. Then I'm going to go through the outline of the original hardness proof from the Aronson-Arkhipov paper from 2012. Okay, now this might be familiar to some people, but the point here is, on one hand, if you're not familiar with this, I want you to at least kind of get a flavor of how you prove these things. But also, it's going to be easier for me to then tell you what were the new things that we had to do in contrast to how they were done in the original work, right? So I'm going to just kind of, the sort of proof template is very similar. I'm just going to focus on what we had to do that was kind of extra challenges in our work. Okay, so let's start with boson sampling. So basically, you can think of boson sampling as both a specific physical device and a kind of computational question, okay? Computational task. So in terms of a physical device, just as I said, just take what Ernesto was describing and scale it up, okay? So you have like n photons, or bosons in general, but photons for concreteness, in m modes, and these two numbers, m and n, are going to be kind of very important, figures of merit. And they interfere through a network of ping splitters, and they come out on the other side. This network is described by some interferometer matrix U, and they come out on the other side, and you monitor all of the output modes, and you detect how many photons ended up in each mode. And you do this over and over and over again, and at the end you're left with some probability distribution over these kind of Fock state outcomes, okay? And this probability distribution is going to be the star of the show, right? So this is the thing that we care about. This is what we're going to define our computational task. So this is boson sampling as a physical device, but as a computational task, then it is just sample from that distribution, right? That's defined as the output of that device. That is a well-defined computational task. And for a quantum device, this is easy, okay? Now notice I'm a theorist, not an experimentalist, so that's why I can say that it's easy. But it's easy in the sense of you're just kind of watching photons in their natural habitat, right? So it's much easier compared to having to do like universal quantum computation. That's the point. But you have good evidence that this is very hard for a classical computer. And the sort of kernel of this evidence comes from the fact that the probabilities are given by permanence of some matrices, and permanent is a notoriously hard function to compute. Okay? So if you have an n-photon experiment, the best algorithms to compute these probabilities, these permanents, take time that goes as n2 to the n. Okay? And notice that the important figure of merit for how hard the problem is the number of photons, right? Not the number of modes. This is going to be important again. And Aronson and Arkhipov in 2012, what they showed was even approximate simulation is hard, right? So even if you allow some error, you say, oh, I don't want to sample from this exact distribution, just something that's close in one norm to it, that's still hard. That was the point. And just kind of brief review of the history. In 2012, we got the first experiments. They're all kind of small scale experiments using 3 or 4 photons at a time. But just kind of proof of principle experiments of this kind of thing. And but things developed a lot since then. The biggest experiment that I found that fits in exactly this template that I described to you is this one by the USTC with 20 photons in 60 modes. Okay, and within the original boson sampling proposal, I think this is the largest experiment that I could find. However, what people noticed was that you can talk about variants of boson sampling where you replace, for instance, the Fock state inputs with like 2-mode squeezed states. And if you move to those variants, then things have scaled dramatically faster. So this is the sort of timeline of these experiments. And I was really taken aback like half of last year when Michal sent me a photo. I think he was in a conference at AQIS, I think. And he sent me a photo of the slides that the Chinese group was presenting this work. And they said like, oh, we did an experiment with 3,000 photons in 8,000 modes. And I'm like, that's like a gigantic leap from the best previous experiment, right? So this thing has increased dramatically faster, right? So it went from like 3 photons in 2012 to 3,000 photons last year. Now, notice the following. There's an important caveat behind all of these results, which is that the theory requires the number of modes to be quadratic in the number of photons, right? And I'll tell you why shortly. But if you look at the ratio between number of modes and number of photons, you know, the number of modes is like twice the number of photons. No one's doing something that's quadratic, right? And if you go to the experiment and says, oh, you know, you have very nice 3,000 photon experiments, but you're just using 8,000 modes, you know, how about you go and do one with 9 million modes? They're going to laugh you off the room, right? They're going to say, that's ridiculous, please never come back. So this is nonsense. And we noticed this and we said, look, you know, this requirement, and we're going to call this the dilute regime, right? So it's the dilute regime in the sense that there's a lot of empty space for the photons, right? There are many, many more empty modes than there are photons. So the photons kind of don't collide too much with each other inside. However, you know, this is basically in the original paper for pure theoretical convenience. And I'm going to tell you why. Right, so it's just simpler to prove things in this limit, but there did not seem to have any kind of fundamental reason why you would require this. And then, so this is what we did, right? So this is our contribution. Our contribution is we give comparable evidence that boson sampling remains hard, even when the number of modes is only twice the number of photons, okay? And this is the saturated regime. So saturated because now, you know, kind of half the modes are occupied with photons. So they collide a lot inside the interferometer. And now this is much nicer, right? Because this is exactly the range in which experiments are working right now. Okay, and this also works for Gaussian boson sampling, which is what these experiments have done. Okay, so this kind of, you know, retroactively justifies theoretically what the experimentalists have been doing. They don't particularly care, but, you know, we are theorists, we like that. So, okay, so let me give you this kind of outline of the original hardness proof of Aronson and Archipel, right? So as I said, I want you to get a flavor, but also because, you know, I'm just going to focus later on what is different when you have this saturated regime. So we're going to start working in this kind of dilute regime, and I'll tell you why. So I'm going to break this proof, and it's going to involve a little bit of complexity theory. I try to make it not too technical. But I'm going to break it in 3 steps, right? And all of these kind of random circuit sampling proofs and fermion sampling and boson sampling, they all kind of are more or less the same outline. So we're going to have 3 steps. Step 1, you're going to start with the assumption that there exists an efficient classical algorithm to simulate the device, right? So you suppose it exists. So suppose there is some classical machine here that takes as input a description of the experiment, right? So it takes as input the unitary matrix that corresponds to the interferometer. And, you know, maybe behind the scenes, the machine is computing all of that probability distribution. Maybe it's not, I don't know. But the task that the machine is performing is just producing samples, right? So you press a button, it spits out a sample from this distribution here. That's close to the ideal one predicted by quantum mechanics. So that's going to be our initial assumption, right? When you have this, we then use something called Stockmeyer's algorithm. And this I'm just kind of reproducing the original proof by Scott Aronson and Alex Archipel, right? So use a thing called Stockmeyer's algorithm. And basically what it says is if you spring a little bit of magic powder on your classical computer, right? So just a little bit of magic powder, it now can compute the actual probabilities. So basically what this says is that if this machine exists, then there exists a BPP with NP classical machine to approximate the probabilities. If this doesn't mean anything to you, don't worry, right? The important thing here is that this is a super powerful classical machine that has some amount of magic power, but only moderately super powerful, okay? And I'm gonna tell you, why it's only moderately super powerful is going to be clear shortly. It's going to be contrasted with something else, okay? So it is not about a real world device, it's a super powerful machine, but it's not completely super powerful. Okay, let's kind of set that aside for a moment. Now, step 2 is we need to encode some sort of hard function in the device. But for boson sampling, that's kind of trivial because that kind of comes built in with the description of the device. And basically the idea is, recall what the device was. We have n photons and n modes and some interferometer U here, right? And we want to compute a transition probability from some input state T to some output state S. And that probability is given by a permanent of some submatrix of this big matrix U, right? And I'm going to show you how to construct this submatrix UST because the structure of this is going to be kind of important for our work later on. So basically, here, if U is the big interferometer matrix, what you do is this. So you look at the input, and for each photon in the input, you choose one of the columns of the matrix U. And then you look at the output, and for each photon in the output, you choose one of the rows of this matrix. And where the rows and columns that you chose intersect, that's the submatrix that you care about, right? So this is the matrix whose permanent you're going to be computing, of a submatrix of the interferometer. Okay, now one other thing here that's important is when you have collisions, and this is going to be more relevant when I tell you about our work, but when you have collisions, or like photonic bunching, when you have more than one photon at an output, what you do is just take more copies of that same row, right? As you kind of intuitively expect. Now the thing is, when you take more and more and more copies of the same row, the permanent might become easier, and that's one of the challenges that we're going to have to deal with a little bit later on. Okay, so keep this in mind for later, this will be important. Good. Now, so when you combine all I've said so far, what you have is that these moderately super powerful machines, BPPUs and NP classical machines, can approximate these matrix permanents. Okay? Now, why do you care? Right? So what? How hard could the permanent be anyway? Now the thing is that the permanent, in the worst case, is in this complexity class called Sharpie, which is super extra hard. Right? And now is where I want to make the distinction between moderately super powerful and super extra hard. So if this is the theory, like the structure of these complexity classes, those moderately super powerful machines I told you about are here. But the permanent is a function that's expected to be out of reach even for them. So it's expected to be way, way, way up there, much, much, much harder than even what those magic machines could do. Okay? So, that's why I've been kind of focusing on this kind of only moderately super powerful. Not enough to be able to compute permanence. That's the sort of punchline. Okay, but there's a caveat here that, the permanent is very hard in the worst case. So there are matrices for which the permanent is hard to compute. But what about the matrices that actually appear in the experiment? Are those hard? And at this point, you have to do something that all of these computational advantage proposals have to do as well, which is invoke some conjectures, right? So at this point, you get at a place where we don't know how to prove something, but we conjecture it. And what Aronson and Arkhipov conjectured, this is where kind of most of the magic of these proofs happen. But what they had to conjecture was the following. So before that, they made two choices, right? So the first choice that they made was that this big interferometer U would be hard random. Okay, you want to assume that it doesn't have any special structure that you might want to exploit. But also, you assume this dilute regime that I've been telling you about, right? So the photons are all kind of pretty spread out. And the consequences here are the following. So remember, the interferometer U is the big one, right? But the permanent is going to be computed off the smaller one. Now, the thing is, when you have the big one are random, but when you look at a sufficiently small submatrix of it, that submatrix looks approximately Gaussian, right? Which may look kind of weird, because if the big matrix is unitary, right, all of its rows and columns have to be normalized and are orthogonal to each other, right? But what this says is that if you look at it, zoom in sufficiently close and you look at a sufficiently small submatrix of it, those constraints that come from unitarity disappear. You don't see them, right? So sufficiently small submatrices look Gaussian. But also, these kind of no collision states dominate, right? So you almost never observe two photons coming out in the same mode when you're in this dilute regime. So the combination of these two things is why they chose this dilute regime. And then they proposed two conjectures. The first one was known as the permanent of Gaussian's conjecture, which just says these guys are particularly hard, right? So these Gaussian matrices have some of the hardest permanents to compute. That's one conjecture. And the other one is an anti-concentration one that's a bit technical. I don't want to go into it. Okay. Now, let's combine all of these ingredients. Okay. So when you combine those first two steps that I told you about, what you get is that those moderately super powerful classical machines can approximate Gaussian permanence. When you combine now the two conjectures that I just described, you get that Gaussian permanents are particularly hard to compute. And now when you combine these two things, you get the statement that these BPP within empirical machines, which are only moderately super powerful, can solve these super extra hard problems. And this is considered a very unlikely outcome. And therefore, at the end of this kind of long chain of reasoning, you accumulate evidence against the original assumption, right? So it's something that is not quite a proof by contradiction because it does rely on some conjectures, but you arrive at something at the end which you expect to be absurd. And therefore, this acts as evidence against the original assumption that a classical simulation exists in the first place, right? So this is kind of the outline of the proof. And then at the end you say, oh, therefore, there should not be a efficient classical simulation of boson sampling. That's the whole story, right? And this is kind of how you get there. Okay, so now let's, this was all Aronson Arkhipov 2012, very old. Now let's tell you about what we did. So, now we want to move to this saturated regime, right? So we don't want m equals n squared. This requires 9 million modes. That's silly. So what if we're in this kind of much more normal regime for like experimentalists would like? Well, what you can do is just write a new conjecture, right? If you're going to end up conjecturing something that you don't know anyway, just write a new one and go home, right? Job's done. But that of course is kind of lazy. So we kind of had to do some work to provide evidence for this new conjecture. We are going to have to invoke a new conjecture. That's inevitable. But we wanted to do some work towards giving evidence for it. Now, let me just kind of take a closer look at the original conjecture in the Aronson Arkhipov paper, right? So the thing that they had conjectured there was that permanence of n by n matrices of IID Gaussian elements are sharply hard to compute to high precision most of the time, right? That's the conjecture. And sometime later, some other authors proved a weaker version of this conjecture, right? So you can prove that if you require a very, very, very stringent approximation, the conjecture is true. But the thing that you need for the boson sampling proof to go through is that it remains true even when you kind of relax your level of approximation a little bit, okay? So there's this gap between what you can prove and what you need to conjecture. But this acts as evidence towards the conjecture. That's a weaker version of it holds. Okay. So in our result, the story is going to be the same. So the end take-home message is going to be that we're going to prove that there is a similar gap between what we can prove and what we need to conjecture, but now for boson sampling in this saturated regime. Okay. But the gap is going to be roughly the same size. Okay, so let me tell you what are the new challenges that appear when you're in this saturated regime. The first one, right? And I'm not going to go through the entire argument again. I'm just going to kind of point out what is different. But the first challenge is that the submatrices, they now don't look IID Gaussian anymore, right? The entries are very correlated because remember, before you had this big interferometer matrix and you're looking at a very tiny submatrix of it. Right? And then you can say, oh, the submatrix is sufficiently small that I don't need to care about the fact that the big one is unitary. But now, in this new proof, that doesn't hold, because you're now looking at a very large submatrix of U. And now the fact that U is unitary, the kind of orthogonality of the rows and columns, becomes very evident, right? And this makes all of these entries very correlated. And in this case, in the original paper, you could do a bunch of random matrix theory because the Gaussian ensemble is very well understood. The new ensemble, where the entries are correlated, much less well understood. And that was one of the things that we had to deal with. And the solution there, and I'm going to kind of completely skip all of the technical details, but you can ask me later if you want. But what we had to do is just kind of throw a bunch of random matrix theory at it, plus some amount of a polynomial interpolation. Let us show that these correlations that appear in the entries of the matrix do not spoil the computational complexity. So it remains hard, even though the matrix, the ensemble, is not the Gaussian ensemble anymore. That was one thing, right? So this required a lot of random matrix theory that was tailored specifically to this ensemble that appears in the experiment. That was the first challenge. The second challenge, collisions are not unlikely anymore now, right? So now your permanents have a bunch of repeated rows, because it's very common that 2 or 3 or 4 photons are going to end up in the same detector at the end. And these collisions are a problem, because we know that if there are too many collisions, the permanence does become easy, and you don't want that. So what we had to show was 2 things. First of all, a bunch of combinatorics to prove that collisions are not, they are very common, but they're not overwhelming, right? So your output space is not dominated by output with a lot of collisions, even though they do happen. And on the other side, we have to prove that the typical number of collisions that do happen, which is not gigantic, also does not spoil Sharpe hardness. So we had to prove that permanents with repeated rows are still hard to compute. That was the other thing that we had to prove. And the third kind of challenge that appeared was that the outcomes, they don't look the same. So all of these computational advantage results, they rely on a thing called hiding. And this hiding property is that, all of the outcomes are kind of equivalent in a sense. They're kind of, not identical, but they're kind of indistinguishable from each other in a sense, because the ensemble has some sort of permutation invariance. But here, that doesn't happen, because when you have collisions, like an outcome where 3 photons ended up in one mode is very different from one where 2 photons ended up in one mode, and so on. So now you have like an exponentially large number of equivalence classes of these outcomes. And this required changing the template of the proof a little bit. So we had to go back and kind of tighten the screws on the Stockmeyer's algorithm a little bit to take into account this possibility, which was not in the original proof. Okay, so put all of this together. What we did was we defined a new problem, which is subunitary permanent estimation with repetitions, or super. And basically, it just says the problem is compute the permanence of these matrices that appear in the experiment, basically, right? And what we show, our main result, is that this problem is Sharpe hard up to some additive error that's very stringent, right? And this remains true for Gaussian boson sampling as well. So, in the big picture, what we showed was, there is a weaker version of our conjecture that holds, and we proved this, but we still need to conjecture the full version in order for the complexity theory arguments to go through. But the gap between what is known and what is conjecture is of roughly the same size as in the original boson sampling proof, right? So I'm not saying that we proved that saturated regime boson sampling is as hard as the original one. What I'm saying is that both proofs are to kind of, they have evidence to the same standards, let's say. There's the same level of evidence backing them up, but they're kind of still logically independent from each other. Okay, so this is what I wanted to tell. Just kind of quick recap of everything. We defined this problem super. We showed that it's Sharpe hard to approximate these things to very high precision. We need to conjecture that it remains Sharpe hard when you relax that precision a little bit, but the gap is similar to the original standard boson sampling result. But, it's still an open question like all of these quantum computational advantage proposals. But now we're in a very kind of experimentally friendly scenario, right? Rather than m equals n squared, as long as the number of modes is at least twice the number of photons, you're happy. There are important open questions. One of them is that, even though this is all true, it's still the case that maybe classical algorithms can leverage these collisions that happen to compute slightly larger permanents. So, if you ask about what is the sort of finite size of your experiments that is required to show a computational advantage, maybe it's not exactly the same number of photons or something like that. We did not look at that at all. Like, what is the consequence of this for finite sized experiments? We still need to make everything more realistic. So, noise, losses, what if you only have threshold detectors rather than number resolving detectors? We have not touched this problem yet, although I think this is an important question. But the one thing that I think is more important, and maybe this is counter to everything that I've been telling you a little bit, is like, how can we use this to move the field forwards, right? In the following sense, I think that this concept of unverifiable computational advantage is past peak usefulness a little bit, right? I think, we have very large experiments, but if like next year someone says, oh, I now have a boson sampling experiment with 30,000 photons, you can say, yeah, sure, good for you, but what are you going to do with that? Right? You can't even tell whether the experiment, like it's already getting very hard to tell whether the experiments work in the first place. So you have like 30,000 photons, you don't know what that's useful for. It's getting hard to verify that that works. So I think like, this idea of unverifiable computational advantage was very important over the last decades to kind of move the field forward and make larger experiments and motivate those experiments. But I think it's a little bit past its prime now. I think at this point we need to ask, yes, what can you do with it now? Right? What is the next best thing that you can do that's going to sort of move you towards something that's more like universal quantum computation, fault tolerance, and so on? Right? So I think like some of our intermediate results could be useful for that, of like thinking more in terms of what are the interesting things that you can do with this rather than just pure computational advantage. Okay, so thanks.
Thank you, Daniel. Any questions?
Jens. Oh, thanks.
The first question is there any hope to get like a matching bound that you need the linear regime and that we have like field photons you get classically simulatable even for sampling and not only for expectation values? And the other one, I mean, I see that it's much more experimentally friendly to be in the linear regime, but can one kind of cook up an argument that you're also more robust to noise in that regime? Because ultimately that's the main battle, right? To fight noise and get sufficiently deep circuits. So can you kind of conjure up an argument that having fewer photons is a good thing?
Okay, so about the first question, like some matching bound from the other side, right? So the thing is, if you have more photons than modes, right? Then you're asking a different question, right? Because all of these things assume that you have like this standard input where it's just one photon per mode. Now if you say, oh, if I have like twice the number of photons, the number of modes or something like that, then now you do need to kind of choose a different input, and there's a bunch of collisions already at the level of the input. So then the question starts becoming a bit different. If you only have like a logarithmic number of modes, then for sure it's classically simulated, right? So that's definitely, if your matrix only has like a log different number of rows, then it definitely becomes easy. But I don't know anything beyond that. Like even for Gaussian boson sampling, where the number of photons is not fixed, maybe that question is more natural, but we don't know. We don't look at that. But I think that's an interesting question. It's interesting that this kind of matches for instance, if you look at like KLM, right? So what you would need for universal quantum computation, for instance, and you kind of look at the sort of density of photons at the input, it's also kind of number of photons is kind of half the number of modes. So it kind of matches, but it could be that you could do better. I don't know. The other thing about robustness to noise, we have not touched that yet. The one thing that I can say that's kind of trivial in a sense is, as long as you have to do kind of hard random interferometers, right? Reducing the number of modes also reduces the depth of the interferometer, right? Because the depth of the interferometer is linear in the number of modes. So, and reducing the depth reduces the losses, right? If you don't have to make them, if you're happy with smaller interferometers. I mean, that's why the experimentalists have been doing this range, right? They're not going to do 9 million modes. So that's kind of part of the answer. But for instance, there's a recent result that shows that you can get away with boson sampling with like logarithmic depth. They have some argument along those lines, but there it's in the dilute regime as well. So I think that there's an interesting question there. We can kind of mix and match our result with theirs and show that, in the linear regime and with only logarithmic depth, it's still hard. That maybe there's one point that would be really good in terms of losses. But all of those things are very recent. That's one thing I wanted to look at, but we didn't do that yet. Yeah.
Other questions? At the back there.
Cardio.
Yeah, sorry if this doesn't make any sense at all, but I was wondering when you said that the collisions aren't overwhelming. Why can I just make a condition and then look just at the outcomes that are collision free and try to recover the condition?
Well, the problem is that
Like
if,
make a post selection.
Sure. The problem is that in this case, for instance, if you only look at collision-free outcomes, they are an exponentially small fraction of the output space. So you would have to wait a lot of time before you observe even one of them. That's basically the problem, right? So collisions, they're not overwhelming, but they are extremely common. And you would have to wait a lot of time to see an outcome that doesn't have any of them. Basically, that's the sort of high-level answer, I think. Nope.